Welcome to Mark's Academy of Science. Geology and Earth History, the study of the age of the Earth, Part 1. Oh, wow! How did I get here? Oh man, my science table is all set up, all ready to go. It's amazing how well teleportation works these days. Okay, well, we've already got our candle lit for the first demonstration. Now, we're going to talk about the age of the Earth and all of its serious implications. And you know, when you walk into a room with a candle already lit, do you know how tall that candle was from the very beginning? No, you don't, do you? Nope. As a matter of fact, if we were to measure this candle, and let's say it was a foot long, we have no idea how long this candle's been burning. Maybe it was a foot longer. Maybe somebody lit this candle 3-4 days ago. And maybe the candle was this long. Or maybe it was this long or tall. Maybe it was this tall. Maybe it was this tall. We have no idea how long this candle has been lit. We're going to measure this candle. And look there. It is 9 inches tall. Okay, so what we're going to do is we're going to leave and we're going to come back at exactly the same time tomorrow at 3 o'clock in the afternoon, and we are going to see how much it has burned down. Okay, here we are 24 hours later, and we are going to measure the candle again. Now remember, yesterday, 24 hours ago, this candle was 8 inches tall. Now let's measure it again and see how far the candle burned down in 24 hours. Let's check this out. Oh wow, okay, it went down to 3.5 inches. So we went from 8 inches to 3.5 inches. Okay, so it burned down 4.5 inches in 24 hours. Now, here's the thing. Can we dogmatically say that this candle will burn 4.5 inches in 24 hours? Well, I don't think we can be dogmatic about it, because somebody could have come in here, blew out the candle, and waited for a while, and then decided, oh, we better relight this candle. Or it could be that one of the big doors here opened up for a while, and the wind could have come through here and gave this burning candle oxygen. And of course, the more wind, the more oxygen, and the faster it's going to burn down. So there's really no way for absolutely for sure just how fast this candle would burn down in a closed system. See, this is like dating a rock. You see, you never know how much uranium is in a rock from the very beginning. Okay? We don't know what it started out with when that rock solidified. Hey, welcome to Mark's Academy of Science, Geology and Earth History. All right, well today we are going to learn about the age of the Earth and why it's so important. We're going to learn about the scientific implications of the age of the Earth. Now, there are some people who call themselves scientists who claim that they know for sure that the age of the Earth is billions of years old. But is that really true from a scientific perspective? I will tell you, the age of the Earth is probably the most hotly debated topic of all time. I don't know if there is any topic that is more debated. People get so frustrated and angry over this one topic because, you see, here's a fact, people. This is something we can all agree with. If the Earth is young, then it had to be created. If the Earth and the universe are billions of years old, then it puts the creation into question. You see, if the Earth is young, then it had to be created, and so therefore there is a God with rules, with absolutes, and many people do not want to live under those absolutes, and of course that's why you have all the chaos and trouble in this world. We've got to learn a little bit about chemistry before we start talking about radioisotope dating, uranium-lead dating. And so you will want to get out your sheet called the Periodic Table of Elements. I have the marked up one. This is the teacher's edition. And so the periodic table of elements, and the way you will know that you do have the right one is the first question is the atomic number tells us how many blank there is in an element. Okay, so before we get into that, I just want to explain or defined, well, what is an isotope? Because we're going to talk a lot about isotopes. Okay? So in order to understand what an isotope is that an isotope is a variant of the same element. So for example, you have carbon. Okay, so carbon has three main isotopes. There's carbon 12, 13, and 14. Carbon 12 is the least radioactive. In fact, I don't think it's radioactive at all. Carbon 14 is more radioactive, and so it is constantly breaking down, and it has a half-life of 5,730 years. And so carbon 14 at the most will last 60,000 years, and we use carbon 14 to date organic material, for example, like fossil bones, things like that. Anything that is organic, something that was alive, or like leaves and things like that. Anything that might have carbon in it. Okay, so that's what an isotope is. An isotope is a variant of the same element. So you have like carbon 12, 13, and 14. However, we need to define it even more. An isotope is where you have the same element, but each of the same kind of element has different number of neutrons in it. You change, for example, like let's say you have carbon 12. If I change the number of protons, then I have changed the element. It becomes a different element. All right, when I change the number of neutrons, it stays the same element, but then you have a different isotope. Okay, so that is what an isotope is. It's just a different number of neutrons in the same element. Okay, so protons are positively charged, electrons are negatively charged, and neutrons are neutral. Okay, it's very simple to remember that. All right, so protons are used in chemistry to change the type of element. Electrons are used in electrical engineering, in electronics. You know, electrons are about flowing electricity, getting electricity to flow. Also, electrons are used for bonding. Now, okay, I better qualify that or clarify that. We're not weird here in this class. Well, let's see, I need to take off my sunglasses. It's about bonding, but not what you think. Okay, we're talking about bonding different elements to create chemicals, you know, that kind of stuff, that kind of bonding. That's what electrons are used for. Protons, of course, are about changing one element into a different element. Neutrons are about making some big bombs, okay, nuclear energy. Okay, let's move on to our sheet here, and we are going to start with question 1. And question 1 is the atomic number tells us how many blank there is in an element. Now when you look at the periodic table of elements, there's going to be this word called atomic number. Okay, so the atomic number is just simply how many protons you have in an element. Alright, so carbon 12, 13, and 14 are all going to have the same number of protons, but different numbers of neutrons. Okay, so carbon 12 is going to have 6 protons, and it's going to have 6 electrons. Okay, and then carbon 14 is going to have 6 protons and 8 neutrons. All right, now, number 2. Potassium has how many protons? Now there's a reason for why, you know, we're talking about potassium and radium and hydrogen, because this all has to do with dating a rock. Now wait a second, that doesn't sound right either. Okay, we're not going to date a rock. Okay, we're not weird in this class or anything. No. Talking about age dating a rock. Okay, age dating. So we're going to learn how to date a rock, but we're going to learn how to age date it. Okay, we want to make sure that's cleared up. So, potassium. How many protons are in potassium? Well, we have 19 protons. There's 19 protons and 21 neutrons. Okay, how many electrons does argon have? Well, argon has 18 electrons, so if it's got 18 electrons, how many protons does it have? It's got 18 protons. Okay, because you're going to have the same number of electrons as you will protons. Okay, how many neutrons does radium have? 138. 138 neutrons. Now, let's talk about the atomic, or the mass number a little bit. So the mass number for radium is 226. 226. Now, what that is that is the number of protons and neutrons added together. So when you add the protons and neutrons together, you come up with 226. So you have 88 protons and 138 neutrons. That comes up to the mass number of 226. Okay? Now, if I'm going too fast, you can always put me on pause. You can rewind me. You know, you can do whatever you want to do. Just don't shoot the TV screen or your computer screen or whatever. Okay, number 5. How many isotopes does hydrogen have? Well, there's 3 main ones, and that's tritium, deuterium, and hydrogen-1. Hydrogen-1, it's got 1 proton, 1 electron, and 0 neutrons. Okay? Let's see, so tritium has 2 neutrons, deuterium has 1 neutron. How many neutrons does elemental hydrogen have? 0. That's number 6 on your page, number 6. Okay, so the mass number in the periodic table of elements tells us what? How many neutrons that are in an element. That is your mass number. Okay? And then your atomic number tells you how many protons you have. So if you have 6 protons, you're going to have 6 electrons. Okay, so now what I want us to do on this sheet here is I want us to skip down, because we're going to mainly emphasize carbon-14 dating first. Okay, so what I want you to do is I want you to skip down to number 15 on your paper. And it says, what is potassium-argon dating used for? Potassium-argon. Now, of course, uranium-lead dating is also used for the same thing. It's used for rocks. Okay? Now, we're kind of getting ahead of ourselves, but it's used for rocks. For example, like this one right here, this granite. Okay? Because granite is an igneous rock, volcanic. Okay, at one time it was fluvial, it was fluid, and it cooled down, and once it cooled down and it got hard, instantly, it's right in there where it was fluid, and where it's solidified is where the clock gets reset. Now you got to remember that. Now we're not going to get into that right now, but just remember that potassium-argon dating and uranium-lead dating is used for dating rocks. Carbon-14 dating is used for dating like bone material. Okay, things that are carbon. However, here's the problem. Here's the problem. If I were to take this to your typical secular university today, this dinosaur bone, and I were to say, would you date this with carbon-14 dating? They would look at me and just laugh. Why would we date a dinosaur bone with carbon-14 dating when it only has a half-life of 5,730 years, which means it's only good for 60,000 years? You see, your typical university professor that believes in evolution is going to say, well, this dinosaur bone is millions of years old. We would never date it with carbon-14 dating. You see, the truth is, people, there is carbon in the dinosaur bone, and that's what they're afraid of. That's why they will not date a dinosaur bone with carbon-14 dating, because they're afraid they're going to find C14 in here. If they find C14 in the dinosaur bone, that means it's not even 60,000 years old. And you see, that really hurts their evolutionary theory, because you see, it all goes back to this one thing. If the Earth is young, then it had to be created. If the Earth is billions of years old, then it puts the creation account into question, if it was even created. Okay? So, carbon-14 dating is used for organic material. We date organic material with carbon-14. Okay? So number 16 on your page, carbon-14 dating is used for fossils. The half-life, now this is number 17, the half-life of C14 is 5,730 years. Okay, next page. Number 18. How many protons and how many neutrons and how many electrons are in C14? Well, you know what it is by now. 6 protons, 8 neutrons, 6 electrons. And C14 is radioactive, it breaks down, and it's an isotope. Okay? So, number 19. So, number 19, carbon-14 decays into N14. That's nitrogen 14. So here's what happens. The sun bombards our upper atmosphere. And when it's doing that, it turns N14 into carbon-14, into isotope carbon-14. Okay? Now N14 is non-radioactive, stable element. Okay? And, okay, so just remember that for now. So now number 20, nitrogen 14 has 7 protons and 7 neutrons. Number 21, how many isotopes does elemental C12 have? Now, I just got done saying that carbon has 3 main isotopes, carbon, 12, 13, and 14. But now how many isotopes does elemental 12 have? Elemental carbon-14 have? Well, it has 15. Now, my major is not in chemistry. I minor in that, so I'm not really into chemistry as much as I am in geology, but I'm kind of helping you understand here that chemistry and geology, they overlap one another. You've got to actually know some chemistry if you're going to get into geology. Okay? So number 21, how many isotopes does elemental 12 have? It's 15. Okay, so we're going to now talk about carbon-14 dating and how that works and why it's not accurate. It's not accurate at all. In fact, like I said before, evolutionists, they're really afraid to date a dinosaur bone or a leaf or like a trilobite. I think, let's see if I remember right, according to the evolutionary geologic column, the trilobite, they say, is like around 400 or 500 million years old. That's kind of weird when they say that it's that old. You know how old 400 million has to be? 400 to 500 million? Why, that's such a huge number, nobody can even understand it. And yet when I look at this trilobite fossil right here, I see perfect design. I mean, there is no wear and tear on this dinosaur fossil. It is immaculate. It is defined, very well defined. I mean, some people, they say, well, why do fossils look old? Well, who decided when a fossil looks old? I mean, fossils, they don't look old or young. They just look like a fossil. I mean, here's a fossil that's in perfect condition, perfectly preserved. It's like it lived yesterday. And they want to tell me that this fossil is 500 million years old? That's a little bit ridiculous. I'm sorry, I don't have that kind of faith. My faith is not in something that I can't see, something that's not there. Okay, today we're going to talk about carbon-14 dating and how it works and why it really can't be trusted. Okay, and before we get into the lesson, I want to refer a book to you. Now, this is not one of our textbooks, but this is a great resource. The book called The Young Earth, written by John Morris. Now, you can get this from ICR or Answers in Genesis. There's a lot of different creation science organizations that sell this book. You can get it off of Amazon, actually. But this is one of those books that when you get done reading it, it's like, wow, I can't believe there's a whole nother side of the story about dating rocks or age dating rocks and the rock layers and fossils. You know, once you start reading this book, it's hard to put it down because you realize, you know, you're kind of being lied to from the mass media, and the public schools, the universities. They're not telling you the whole story. They're not telling you the other side of the story. And of course, our textbook that we are using, The Global Flood, this book actually helps a lot too with telling the other side of the story. Actually, these two books go together real well. And I would like to have used this book in our course, but you know, it just it makes everything so cram-packed when we got two textbooks and we're trying to get them done in a 9-month period. But I would suggest that you get that book called The Young Earth if you're really into science. You really like hearing the other side of the story. You say, you know, I'm just kind of getting tired of being lied to. I'd like to hear the other side, you know. Okay, so what we're going to do here is we're going to take this big test tube, 1,000 milliliter test tube, full of water, and we are going to pretend that this represents carbon-14. Okay, now first of all, understand this. Carbon-14 is made in the upper atmosphere by the sun bombarding the upper atmosphere, turning N14 into C14. So N14 has 7 protons. Okay, so the upper atmosphere turns the N14, which has 7 protons, into C14, which has how many? 6 protons. Okay, so N14 into C14. And remember, as I said, that you have a half-life of 5,730 years. Okay? So we're going to pretend that this here is C14. C14 only has about 10 half-lives and then it's all gone. It's kaput. But yet we still have C14 in the atmosphere. Okay? Which is very interesting. You got to remember that. All right. Now, so we're going to pour 500 milliliters of water into this flask because that's half of 1,000. Okay? We're almost there. Okay, so there you go. Now there is half of 1,000 milliliters. So now we're down to 500 milliliters. So that is like 1 half-life. Okay, so it could be said figuratively or metaphorically saying that 5,730 years just went by. Okay, because that's the half-life, a half-life of C14. So now we're going to pour 250 milliliters because, you know, what's half of 500? 250, right? Okay, so now we're going to go down to 250. Yep, that's close enough. 250. Okay, so there's another half-life that's just taken care of. All right, now what's half of 250? 125, right? So let's go down to 125. And you'll notice each time I pour, it doesn't take near as long because you have less of it. All right. So there you go. Now we're down to 125. Well, now what's half of 125? I believe it is 66.5. So now we're going to go down to 66.5. Yep. Okay, so we're just going to say 66. So what's half of 66? 33. And you see, you just keep doing this until you're out, until you're completely out. All right, so now we're out. Okay, so now, like I said, there's about 10 half-lives in carbon-14. Once you have had 10 half-lives of carbon-14, well, then you've run out. There's no more carbon-14 left. It's gone. Well, guess what? We still have carbon-14 in bones today. We still have it in the atmosphere. So if I date this fossil right here, this dinosaur fossil, and it still has carbon-14 in it, well, what does that say? What does that mean? Well, that means that the dinosaur bone has to be less than 60,000 years. That's exactly why the evolutionists, they don't even want to try to date a dinosaur bone with carbon-14 dating. they're afraid they're going to find carbon-14 in the dinosaur bone. Because you see, they're very dogmatic that all dinosaurs died off 65 million years ago. And sometimes they're arrogant enough to actually believe that they know for a fact that all dinosaurs are gone. Well, that's a whole nother story, and you'd have to be omnipresent and all-knowing to know that for sure, that all dinosaurs have died off. And of course, it depends on how you define what a dinosaur is. That's another thing that we should probably talk about in one of these classes. Okay, so carbon-14 is formed when the sun's rays bombard the upper atmosphere, turning nitrogen-14 into carbon-14. Now remember, nitrogen-14 has 7 protons, carbon-14 has 6 protons. Okay, carbon-14 is radioactive. In other words, it breaks down. That's why we have the half-lives of carbon-14 of 5,730 years. Okay, now there's only one atom of carbon-14 that exists with 1 trillion carbon-12 atoms. Okay, now that's something to keep in mind. Now the ratio changes as C14 decays back into N14. According to scientists, this Earth has been here 4.6 billion years. And so they say, well, now that we have an equilibrium now. We have just as many carbon-14 atoms that are being made as there are carbon-14 atoms decaying back into N14. Okay? That we have reached this equilibrium, and it would take about 30,000 years to do it. Well, now further research, and they're not telling you this in the news media, they're not telling you this in the secular schools. They have never proven that. In fact, it has now been proven that this equilibrium has never been reached. There's not an equilibrium of as many carbon-14 atoms that are being made as there are carbon-14 atoms decaying back into N14. That equilibrium has never gotten there. We don't have it. So you know what that says? That says right there, this Earth is not even 30,000 years old. The atmosphere is not even 30,000 years old. So if that makes you think. So you already know, okay, we got a problem here. Why carbon-14 dating is not reliable. All right, so now, when carbon-14 is made, becomes part of the C12, there's this ratio, okay, of C14 and C12. So you have one carbon-14 with every 1 trillion carbon-12 atoms. Okay, so you have that ratio, all right? So, as a plant breathes through photosynthesis, it makes that carbon-14 C12 ratio part of its system, okay? Now, animals come along, and they also breathe in that ratio. They also eat off the plants that have that ratio, and the animals make that ratio part of their system. So now the plants have the C14, C12 ratio. The animals have this C14, C12 ratio in them. All right, so let's say a plant dies. When the plant dies, that is when the C14 in that plant starts to return back into N14. Now that's when the clock starts, so to speak. So it is said that when you understand what the ratio is, after the animal dies, one can get an idea of when the plant or animal ceased to exist, when it died, and when it ceased taking in this carbon-14, carbon-12 ratio. Okay? So now it is said that you can then determine how old that fossilized bone is. Well, here's the problem with that. Here's the problem. Many processes such as groundwater leaching into the specimen or bacterial action can actually alter the contents, the concentrations of the parent or daughter material. Now that's one thing we haven't talked about yet, the parent and daughter. So the uranium would be the parent material, that's what it starts out with, and lead would be the daughter material. So when it comes to carbon-14 dating, they would say hydrogen 14 would be the parent material and it turns into C14, but then the C14 turns into N14. If you have groundwater that's leaching in to like the bone material, the animal, the plant, and it's leaching in these impurities, it's going to throw the date off. That's why you cannot trust C14 dating. Besides that, remember the example of the candle. Okay, you come into a room like this and you see the candle burning. Okay, well, how tall was that candle when it was first lit? Well, we don't know, because there's no way to know that, because there was no eyewitness accounts. So there's no way. All we can do is take a measuring tape right now in the present, because this is in the present. We measure the candle, and of course it's a lot shorter now than it was a few days ago. If we were to take a measurement of this candle and just say it's a foot long right now, and then we come back 24 hours later and measure it and find out that 1 inch burned down, well, all we know is that in 24 hours 1 inch of the candle burned down. But we don't know the processes that took place in those 24 hours when we were gone and we weren't observing the candle. I mean, somebody might have come in here and burned out the candle and then relit it. Maybe there was a draft in the room at one time, caused the candle, the fire on the candle to receive more oxygen because of the draft, and it caused the candle to burn down faster. See, there's all of these things that you have to consider that can throw off your measurement as to how old a sample might be. Okay, so there is the problem. Here's the next problem. Many times when an evolutionist will date a rock or a bone and they don't get the date that they want, the date is too young, they will just automatically claim, oh, well, it's contaminated with something. And that does happen. That happens a lot in the science lab. Okay, well, I hope that this helped you to understand C14 dating better. There's a lot more on it, and I would highly suggest that you get this book here called The Young Earth, because this explains it in a whole lot more detail than what I explained it in. Okay, so let's review real quick. So plants through photosynthesis makes this ratio of C12 to C14 part of its makeup. Then animals eat the plants and make the C12-C14 ratio part of its makeup. When the animal or plant dies, it ceases taking in this ratio of carbon. So carbon-14 begins to decay back into N14, thus changing the ratio of C12 to C14 over time. By measuring this ratio after the animal dies, one can get an idea of when the plant or animal ceased taking in that carbon. But here's the problem. Many processes such as groundwater leaching and bacterial action can alter concentrations of the parent or daughter material carbon ratio. So in other words, if you have impurities that are leaching into your sample, then that is going to throw your dates off. And here's the thing that a lot of evolutionists do. If they don't get the date that they want from like a bone or a rock, if they don't get the date that they want, they just naturally assume that they have an impurity in their sample. Okay, and so you can tell there's definitely a real bias there.